Hello, pre-calculus. As promised, you have a video for all things 1.1. So this is our first video of pre-calculus ever. Let's get to it. So I'm going to go over the examples that I was able to go through in class just so that we're documenting it on a video and it's there for all time on YouTube. So here we go. We already talked about how to sort of like decode what's going on here. They're just telling us that x is negative and y is positive. And then for number one, we went through these and said, plug a negative anything into the x and a positive anything into the y. So the idea was xy is basically like saying a negative times a positive, what would that be? And it's going to be a negative. So I'll put n for negative, p for positive to keep time down. So it's n. Right? When we talked about x squared times y, which is a positive number, you square any number, you take it times itself, it's going to be positive. So negative times a negative is going to be a positive, which is going to be multiplied by that positive number. A positive times a positive is a positive. So we're good for A and B on number one. Number two, we've got, 1C. A negative value divided by a positive value added to another negative value. So a negative divided by a positive, negative, plus another negative, because of course order of operations says division must come before addition. A negative plus a negative is always going to be like a more negative answer. So negative for part C as well. All right, and then lastly, you've got a positive number, and I'm subtracting a negative amount from that. Anytime we're trying to take something like 5 minus negative 4, it's basically turning into an addition problem. So, if you're starting out with a positive 5, it's going to create a positive here as well. So, all plus means positive. Yeah, we did number 3. Negative 7 is definitely smaller than negative 4. Further you go left on the number line, the smaller the numbers. This was really cool. We talked about it in class. Again, pi is approximately 3.14. And 1.5 is exactly 3 over 2. That makes it really easy when you look at it from that perspective. Sorry, the video's kind of muddy, but I think you can see if the denominators are the same, the tops can easily be compared. There's where the 3.14 goes. Root 225 is exactly 15. The square root of 225 equals 15. All right, number 5. By the way, I'm not going over every single odd problem on here. It's just I like this first group of problems. All right, 1/11th is actually a repeating decimal. It repeats to 0.09 repeating. So this is 0.090909, which means there's more 09s on the left than there are on the right, making it of greater value. So this should be greater than. 2/3 is 0.6 repeating. There's definitely a ninths and a thirds pattern where like 1/9 is equal to 0.1 repeating, 2/9 is equal to 0.3 repeating. Once you get up to 6/9, which is 2/3, you're up to 0.6 repeating. So this is 0.6 repeating. That means that after the third 6, there's a bunch of other 6s, which means there are those 6s that exist here but do not exist there, which means it's got more value, which means this is bigger than 0.666. All right. And then the last comparison here, 22 over 7 compared to pi. 22 over 7 sometimes is used as an estimate for pi, but when you actually divide it out, 22 divided by 7 comes out to be 3.1, 4, still the same as pi, and the 2 is where the 2 deviate. Pi is 3.141592653, dot, 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 dot. And this one is 3.142. So 3.141 versus 3.142. Definitely 22 over pi is going to be the larger amount. All right. Let's jump to number 13. So, you guys can follow along in your textbook. We are on page, I think we're on page 13, 14-ish. I'm sure you can figure it out. All right, I can't scroll down on this computer. This is the one that's actually doing the recording. All right. So we kind of got to zoom into down here. Hopefully everybody can see that okay. It's number 13. All right, we have 4 minus pi, pi minus 4, and root 2 minus 1.5. They're telling us to rewrite the number without using the absolute value symbol. All right, what the heck do they mean about that? Well, if it's just a simple computation, like if you look at number 9 above here, like number 9, you got negative 3 minus 4. That's pretty much negative 7 inside of the absolute value bars. The absolute value bars are basically saying whatever's inside, take the positive amount of it, and that's what you give as your final answer. So like 9a would be, it's ultimately going to be 7, because it's the absolute value of 7. This is absolute value of negative 5 is 5, minus absolute value of 2 is 2, 5 minus 2 is 3, and this would be 7 plus 4. Okay, that'd be 11. And that's okay. I mean, you can come up with like a whole number answer on some of these. But on these in particular, it's sort of saying like, pi is a never-ending decimal. I can't actually come up with the exact answer for that, but I can write an expression that's way more, what's the word? It's just accurate and doesn't need the absolute value bars. So think about pi. Pi is 3.14 here. I'll put it off to the side where we've got some whiteboard space. Let's see, does that work? It does. All right, so when I take 4 minus 3.14 dot, 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 I have a positive number because 3.14 is less than 4. So if I'm taking away 3.14, the thing inside the absolute value bars is going to be positive. I don't need to express this answer with the absolute value bars. So what they're getting at with 13 part A is that your final answer should be 4 minus pi. You don't need the absolute value bars. It's unnecessary because the thing inside is already positive. Now on the flip side, here's what they do. They reverse them. They say take the absolute value of pi minus 4. Now pi minus 4 is going to give you, it's going to give you a negative number for sure. It's 3 point something minus 4. Small number minus a bigger number means it's going in the negative direction. But I don't know if you guys noticed this, but it's taking the same difference between these two, which means whatever you get here as a positive number is what's going to happen inside here as well. So what the textbook writers are wanting you to know, to figure out, is that the absolute value of pi minus 4 is the same thing as 4 minus pi. They both give you the same answer. It's just one's negative inside of the bars. All right. And then the last one, root 2 minus 1.5. I think they're getting at kind of the same idea here of, I can't actually express root 2 unless I do like never-ending decimal type behavior. But okay, I should be able to compare 1.5 to any square root. And the reason is because I know what 15 squared is. 15, we just talked about it on a previous example, remember? Remember? 225. 225 is 15 squared. So technically 1.5, all right? Try to stay with me on this. Is that still showing up on the screen? It is. 1.5 is the square root of 2.25. Whoa! All you got to do is multiply the number by itself to get the equivalent square root. So when you see root 2 minus root 2.25, it's kind of revealing that, hey, 1.5 is the bigger number. You're subtracting the bigger number, which means that this is going to be a negative amount inside the bars. So all you got to do is flip them around and say this is 1.5 minus root 2. I don't know. Okay, so that might have been really confusing. I don't feel bad if you're kind of scratching your head on that one. Just the whole idea of why do they want us to know that? It's that they want us to play around with this concept of, hey, do you know that absolute value bars mean a lot more than just take some things away? Because once you start throwing variables in the mix, we have to start thinking outside the box with things like that. All right, what's our next example for video notes? I put number 14 in there. I'm going to skip that one. I feel like I made my point on this last one. If you guys are really confused though still, I can go over number 14 when we get back to class. All right, let's move on. We're not doing 14, but we are doing 17. Where is 17? All right, this is giving us just a little review on the distance formula. So one of the things as a pre-calculus student is all those things that you have to do to, how should I put this? Sorry, somebody was going to try to get in my classroom. Number 17, the distance formula is one of those formulas that you kind of have to start thinking like, okay, I need to commit this to memory because it's a basic formula that keeps happening in a lot of mathematics. So this is the formula that says you take the x coordinates and subtract them, but then you add the y coordinates subtracted too. It's actually the result of the Pythagorean theorem. You know, if I get bored sometime, I might just show you how the Pythagorean theorem and the distance formula kind of are intertwined. So what they're basically saying is, take these coordinates, we're calling them A, B, C. So you're just finding the distance from one point to the next on one of these. So if, on this particular example, they're saying that A equals -9, B equals 1, and C equals 10. So all you got to do is, for part A, plug in -9, 1. We need some room. And then on B, we're talking 110. And then on C, we've got CB, which is 10, 1. And then on D, you've got AC, so -9, 10. So they're basically giving you 4 coordinates based on this information over here. Sorry, hello. And I'm not going to have enough time on this video to complete this problem, so I'm going to stop it now and then restart it. Part 2 coming your way very fast.